Alrighty, what's up guys? Nick here. This section is all about lines. This is a pretty big section, so I'm probably going to split it up, so don't be surprised if there's a gap somewhere in the middle. Anyway, let's get stuck into it. Suppose a line is not completely vertical, and we'll deal with the completely vertical ones later. So it has some kind of slope. So a line is not completely vertical. Then it can be represented as the graph of a function of the form y of x is equal to m times x plus c, where m and c are some fixed numbers and x is allowed to vary across the whole real number line. So our line goes on forever in both directions. So y of x equals mx plus c. These functions are called linear. Why is that? You probably guessed because, as I just said, the graph of them is a line. So line here, linear. Okay, so let's get stuck into it. And the first thing we should do is actually convince ourselves that, yeah, these things actually do have graphs that are lines. To do so, let's start out with the simplest case. Y of x is equal to x. Y of x equals x. You put x into the function, you get x out of the function. Let's go ahead and draw its graph. I think we've already done kind of similar ones to this earlier on, but let's refresh ourselves. So that's the x-axis, that's the y-axis. Suppose now that I put x1 into the function. What is y of x1? Well, y of x1 is simply x1 because I put x1 into the function, I get x1 out. And that means that since the x-axis represents the things that come into the function. The y-axis represents the things that come out of the function. If I'm going to draw a point on my graph to represent x1 going into the function and then x1 coming out of the function, it has to have distance across x1 and distance up x1. So it's got to be that point there where those two dotted lines meet. Those two distances should be the same. Sorry if I drew it a little wonky. Okay, do exactly the same thing with any other point. x2 doesn't really matter. In case these x1s are annoying you, I'll give this a number. Let's call it 3. Well, if I put 3 into the function, then 3 is definitely coming out of the function. And to draw the point on my graph, on the graph of y of x equals x, it has to be this guy here that has a horizontal distance across of 3 and a vertical distance of 3. Okay, if I put 0 into the function, I get 0 out. That's what that point represents. Let's do a negative number. Let's say -2. If I put -2 into the function, then certainly -2 is going to come out. So that's that guy right there. And you can keep filling in more and more points. The more points you fill in, you'll find that it gets closer and closer to basically just this blue line here. And so this is the line y equals x, and it is indeed a line. Slightly off topic, oops. Slightly off topic, but what's this angle here? What is that angle? Well, it has to be 45 degrees. Why is that? Because if I make this into a triangle, then for one thing it's a right angle triangle because that's 90 degrees right there. But another thing, this distance here is 3 and this distance here is 3. So it's actually an isosceles triangle. Angles of a triangle add up to 180 degrees and this one here is 90. These two angles must be 45 degrees each because they have to be the same, and also they have to add together to give 90 because 90 plus 90 is 180. Okay, so that's the deal there. Sorry if we're going a bit off topic, but it's kind of related. Okay, next up, we're actually going to draw the line y equals 1/2 x. How are we going to do that? Well, we're pretty much just going to plot points again. So if I put x1 into my function y of x equals 1/2 x, better write it down, y of x equals 1/2 x. If I put x1 into the function y of x equals 1/2 x, I'm going to get half of x1 out. So half of x1 is about here. Half x1. Sorry, my writing's a bit messy. And so that's gonna represent that action. Actually, that's gonna represent putting x1 into the function and getting half of x1 out. Again, if I put 3 into the function, then I'm going to get half of 3, so 1.5 out. And so this point here, this point 3 and 1.5 represents putting 3 into the function, getting 1.5 out. So 1.5. And again, if you put 0 into the function, well, half of 0 is still 0. If you put -2, struggling to read my own writing there, I think that says -2. If you put -2 into the function, you're going to get half of -2, which is -1 out of the function. So the more, again, the more points you plot, the closer and closer you're going to get to this green line here, which should be straight. It's a little wonky. This is the line y equals 1/2 x. So actually remember there's a 1 here, even though I didn't write it in because x is the same as 1 times x. By decreasing this number here, I decreased it from 1 to 1/2. It actually decreases the slope of the line. It causes the line to rotate around like that, because all of a sudden my y values are only half as big for the same x value coming in. So it causes the line to rotate, and the slope of the line decreases. Similarly, the function, let me choose another color, maybe pinkish purplish, this color, whatever it is. If I draw the function y equals 2x, y equals 2x, y equals 2x. So the function y equals 2x, it's actually going to swing this line y equals x around that way. It's going to increase the slope because I have a bigger, what we're going to call gradient. As the bigger the number is in front of the x, the sharper the slope is. So, well, what we've covered so far are functions of the form y of x is equal to mx, and we discovered that for this number m, the bigger that number is, the steeper the line is, the sharper the slope is, because the bigger the y values are that come out of the function. The bigger the y values are for each x, so that creates a steeper, sharper slope. Just in case, well, I'll leave it to you to confirm that if I have a negative gradient, for example, y of x equals, I don't know, let's just say -1 times x, it's going to look like this. The slope is actually going to be so far around that we're kind of going the other way. So it's going to swing all the way around to here if I have a negative number, a negative gradient. Alright, that's all for this section. Thanks for watching. Make sure you check out the notes. I'll see you back in the next section on lines. Take care for now.